In this video, we're going to consider a topic called average rate of change, which is a great precursor for calculus in looking at an instantaneous rate of change. And we're going to start with an application of this so you can build some intuition before we work with some more generic function type questions. So the first thing we want to look at is an example. Let's make that font bigger. Um, let's say we're asking this question: what is the average rate of change in the population below? And we'll fill in the blank there in a moment. But the first thing I want to talk about is average rate of change. What is that if we're talking about population? Well, the idea is that you're looking at over a time period, how fast is the population growing or declining? So we're looking for a unit of people, because population is measured in people, per year. So you're going to have a calculation involving people on top and a calculation involving years on bottom, because we're dealing with population in this example. So, so let me show you a graph of the population. Um, It'll be a rough sketch here. And we will say, let's see, over here it's going to be the population in thousands. And down here we'll have the year. Okay. And let's say that we want to start at the year 2008. And initially the population is, let's say 2000. And over time, the population is going to grow, and the rate at which it grows speeds up like this. Okay? Something like that. Now, I'm not giving you more details about the graph because I'll specify some information about it shortly. Now, let's ask some questions here. The first question. Um, let's mention here some details about the graph. Note that in 2016, the population was 3.99 thousand. In 2024, the population was 7.94 thousand. Okay. Now we can ask some questions. So question A, what is the average rate of change? I'm going to abbreviate here for space. What is the average rate of change in the population from 2008 to 2016? Okay. And so what we're looking at is from 2008 to 2016. Let's say 2016 is right here. We know you can see that the rate at which the population grows is changing. It starts off slow and then it speeds up. But we're interested in the average rate of change over this entire time period. So what we look at instead is, well, let's list how many people were in the population in 2016. That was 3.99, and it's already in thousands. So I'm not going to say this is 3,990. It's 3.99 thousands. And the way to figure this out is simply to take, well, how much did the population increase? So we're going to look at the change in population because that's going to give us our people change divided by the change in year. And this right here is the big idea. You take a change in what you're wanting to measure divided by a change over a time period. Okay, so population matches people and year is what we're looking at in the denominator. Well, that's pretty simple. So 2016 had a population of 3.99 thousand minus, in 2008, the population was 2,000 divided by, so see, this is going to calculate the difference in population, the change in population by subtracting. And then in the year, we're going 2016 to 2018. So we take the later year minus the earlier year. And now we can do this calculation to get our answer. And that gives us approximately 0.25. So we want to think about what this means. Now, the numerator was thousands of people, right? So the numerator up here is 1,000 people. And the denominator is years. So our unit here would be 0.25 thousand people per year. So the answer might be, if it's 0.25 thousand, that's the same thing as 250 people per year increase. So on average, from 2008 to 2016, the population's increasing by 250 people per year, or 0.25 thousand people per year. Let's try another example. So same scenario here, but now I want to know the average rate of change in the population from 2016 to 2024. So now 2016 to 2024, let's say, is here. And this should be a faster rate of change. So when we looked at the previous example, we were looking at the average rate of change here from 2008 to 2016. What we actually calculated was the slope of this line. This line doesn't take into account changes in rate over time. It's, if it were a constant rate, then it would be a straight line. That's our average rate of change. So now I want to take a slightly different approach on this part, and it's the same exact concept, but a slightly different approach. And we want to look at the slope of the line that connects those 2 points. Well, in 2024, the population was 7.99 or 7.94 thousand, and in 2016 it was 3.99 thousand. So the slope is going to be rise over run. So we're going to take 7.94 minus 3.99. That's going to tell us our rise. Divided by our run, we're going to take 2024 minus 2016 to get our run. And in this case, we get about, let's say 0.49. And so now the average rate of change in the population from 2016 to 2024 would be 0.49 thousand people per year, which is about 490,000 people per year increase. Okay, so that's if it increased at a constant rate, that's what it would be to land at the current population. All right, so that's average rate of change in a nutshell. Let's do some more generic examples with functions so we can see how they compare. Okay, let's find the average rate of change in the function f of x. Find the average rate of change in the function f of x equals negative x squared plus 6x plus 1 from x equals negative 3 to x equals negative 1. Okay, so a bit more generic. There's not context here. Now we're interested in how much does the function change. So we're looking for the change in the function on top per the change in x. And so the idea here, again, is the change in the function is a change in a y value, because the function value is an output, a y value. And so we're looking for a vertical change divided by a horizontal change. So the way to calculate this would be, well, how do we calculate the change in the function? Well, we need to know the function value at the end, which is at -1. So we need to know f of -1, minus the function value at the beginning, which would be f of -3. And then to calculate the change in x, we take the ending x value -1 minus the beginning x value -3. And now we just calculate this value. So f of -1, we plug -1 in for x. -1 squared is +1. So we get -1 minus 6 is -7 plus 1 is -6. Then we have to subtract f of -3. So -3 squared is 9. We get -9 minus 18, which is -27, plus 1 is -26. So we have minus -26 over -1 plus 3, which is 2. So we get -6 plus 26, which is 20. 20 divided by 2 is 10. And that is our average rate of change. Let's take a moment and look at what this is saying on a graph of the function. From x equals -3 to x equals -1. Well, this is a parabola. If we graphed it, f of -1, the function would output -6. So we'll just say it's this guy right here. We'll just say -6. At -3, it outputs -26 way down here. And while this parabola has a curvature to it, we're not interested in the way the function curves. We want to know on average the rate of change. So what we're doing is calculating the slope of the line that connects those 2 points. And we can see that the rise here is 20, going from -26 to -6. And the run is 2, going from -3 to -1. So the slope would be the rise 20 divided by the run of 2 to get 10. And so this function is increasing 10 units per every 1 unit change in the x direction. And that's what this number represents. That is how you calculate average rate of change. Now let's do one more example because there's a different way it could be worded. So now let's try to find the average rate of change of the function f of x equals x minus 1 squared minus 1. And now the thing that's going to change is how we specify the x values. So we'll say over the interval, let's go from 1 to 3. And so this is the same exact type of question we just looked at. This is the same thing as saying from x equals 1 to x equals 3. So if we want the average rate of change of the function, we need to find the change in the function, which would be f of 3 minus f of 1, divided by the change in x, which is 3 minus 1. So f of 3, plug 3 in for x, we get 3 minus 1 is 2, 2 squared is 4, 4 minus 1 is 3. F of 1, we plug 1 in for x, 1 minus 1 is 0, squared is 0, minus 1 is -1. And then on the bottom, 3 minus 1 is 2. So we just get 4 over 2, which is an average rate of change of 2. So this means the function is increasing 2 units on average for every 1 unit increasing in the x direction. That is average rate of change. Again, it's a great precursor to instantaneous rate of change introduced in calculus. It is also very similar to the difference quotient, which is more generic than plugging numbers into the function to find an average rate of change over a particular interval, but that's slightly different.